A very good morning to all of you. So, firstly, I would thank all the participants who have taken the active participation yesterday with lot of queries and the question answer session. We are very happy. And to update you, the all the sessions which were taken yesterday, in fact, all the sessions of this MAM 2021, the videos will be shared with you. So you don't have to worry also. So all the videos will be shared to you through the Atal portal. And the first session for today will be delivered by Dr. Deepa Srinivasan. Very good morning, ma'am.
Yeah, good morning. Very good morning. Thank you.
Okay, so ma'am, this workshop is sponsored by Atal Academy under AICT, and here we are required to have 14 sessions, each session of 1.5 hours, and this will be for a period of 5 years. Here the participants are mostly from masters, PhD and faculty and some industry personnel. We have around 100 participants we have registered, but roughly 70-75 participants are there yesterday. So today also I expect the same number actually. So just before starting Dr. Deepa Srinivasan's talk, so let me introduce her about Dr. Deepa Srinivasan. Dr. Deepa Srinivasan is the chief engineer. She has taken over the role of chief engineer at Pratt & Whitney, Bangalore. Prior joining to this one, she was heading at various divisions in GE Bangalore. So Dr. Srinivasan has obtained her PhD from Indian Institute of Science, Bangalore, and she works enormously and extensively. I should not say enormously, I should say extensively in the area of manufacturing, and she has developed a lot of technologies which are relevant to the gas turbines in aerospace industry. And we are very happy to share you that ma'am has received the Woman of the Year by Indian National for Academy of Engineering, which is by the highest body in the Department of Science and Technology and Minister of Science and Technology, Government of India. Last year, she was awarded the Woman Engineer actually for 2020. Congratulations, ma'am. And with these few words, I request ma'am to deliver her expertise and what are the various case studies which she worked for the last many years in metal additive manufacturing. Ma'am, you have time for 1 hour 15 minutes, and we will have a 15 minutes question answers after that, ma'am.
Sure, sure. Can you see my screen?
Yeah, it is visible.
Yeah. Thank you, Dr. Gupta, for this nice introduction and about the workshop itself. And very good morning to all the participants. So what I'm going to do is I'm going to be sharing some of the challenges involved in actually qualifying metal additive manufacturing in the context of this workshop today in gas turbine components. I have given this talk a few times now through this year. And the genesis of this is based on a review article that I wrote based on my personal experience in terms of qualifying, taking it all the way from the research level to the prototyping level in terms of technology readiness level 3 or 4. And then how do you go into production? And what are some of the things to watch out for? And I will, in each of the challenge that I have experienced, I will share how we overcame that and truly give you a perspective of how scientific interactions with academic institutions, by our students, by our master students, and by our projects with the faculty members, helped us reach this accelerated adoption in the case studies that I'm going to share with you. So, and maybe at the end, I will leave you with some thoughts for research, contemporary research areas, because additive has really grown exponentially in the last 5-6 years, especially in the Indian context, and how we can take this. You have a lined up. Professor Gupta has lined up a series of very good speakers. So how they've been adopted in an accelerated manner. Okay, so before this statutory slide, I'd like to show. This shows you the panoramic view over 6 to 7 decades of Pratt & Whitney's foray in both military engines as well as commercial engines. So you can see like all how materials and manufacturing technologies have actually enabled these advancements in jet engine development, both in commercial as well as in military engines, as I said. together with combustion and propulsion technologies, as well as design and variety of other things that go in to the development of such a complex turbo machinery, such as an aero engine. So you can see single crystal blades, first generation discs. You have thermal spray coatings for actually the hot gas path components. Then you have, so many new advancements. I'm not going to read out every one of them, but really speaking, taking off from this particular slide, if I go to the next slide, slide number 3, this gives you a chronological view of different products, right from 1960s to 2021, where we are today. What you can see here is that each of these products, the main important thing is over 6 to 7 decades, and all these engines are still flying. So that's the whole point. And if you look at the development of an engine itself from one to the other, it has taken at least 1 decade, 1960 to 70, 70 to 80, 80 to 90, 90 to 2000, and so on. So typically, for any new product development, it takes roughly, we're reading Airbus A320, then we're seeing the Boeing 777 MAX, and so on. Each of these takes billions of dollars to actually qualify a single part or a single material or a single manufacturing process. That is a kind of time and effort that is taken for each of the new product development. And given that, that is why this is important. This yellow color, all these are still flying. But today, with additive manufacturing, metal additive manufacturing, we can definitely cut short this product development cycle. If you're going to cut short the product development cycle, then it naturally means you're going to cut short the time and effort involved also. So that is where really I see the emphatic, benefit of additive manufacturing. Definitely all these other benefits your other speakers will also speak about, all of you will also know about. Namely, we're talking about making things hotter and lighter especially for the aerospace industry, whether it is space, aerospace, ISRO, NASA, whatever is it. Anything that is flying up in the air has to be light. Anything that is hotter is going to have several benefits in terms of both the performance, in terms of both the, thrust, that you can get to for flying higher, shorter takeoffs and landing, lower time lower time of return for, maintenance and overhaul. So many benefits it can have. But additive itself is being spoken about in terms of these 5 or 6 performance matrices. As I said, things which are lighter with the design for additive manufacturing, simplification of parts, things, for example, a heat exchanger used to be having multiple operations, welding, brazing, heat treatment, etc., etc. Not to mention not being able to have it in geometries via conventional manufacturing. And then, of course, inventory reduction is a very big thing, because inventory is hardcore cash and so on and so forth. I'm not going to, talk to you. There are other speakers who are going to talk to you about more about the introduction and how it is being, used in different sectors. Mainly, what I'm going to be sharing here is how do we enable the true benefit, all these benefits in early adoption, in fast adoption, and what are the challenges, and how do you go about the R&D towards production for these in these turbo machineries. So if I go to the next slide, this tells you the Pratt & Whitney journey itself in recent times. I don't have the latest of 2021. As I said, this is dated 2020 at least, so it's not very old. And if you look at with respect to the previous performance matrices I showed you, you can have design for additive manufacturing. This is a picture from a military engine, TJ-150 hot section component. True enough, there is a part reduction and a weight reduction. So you see 99% reduction in count and 2 times emission life at maximum exhaust gas temperature, and the operability has not changed. It is equal to the baseline. Similarly, in another commercial engine, this was a military engine example, you see rotating fan module, you're going to have a 105% fan red line. This is terminology for an improvement in performance. And this set of additively manufactured components have seen over 400 cycles and 200 hours of ground tests. Naturally, flight testing has to be concurrent with every aero engine part. Without that, it will not get qualified. So on and so forth. So, and this is an example of an integrally bladed rotor. IBR is what is called. Conventionally, we make a rotor, a large rotor disc, and then we make these blades. Let me show you. I think I have a blade here with me. Let me just bring that out. Yeah. So if you can see, this is the stage 1 high pressure turbine blade. This is from an actual aero engine component sitting in my hand. This is a single crystal blade. So earlier these blades, and if you can see the dovetail, the blades and discs will be made separately. But with additive manufacturing, newly they are thinking of basically to avoid all the losses due to the joining process. It is an interference fit in this dovetail, and it's highly risky, isn't it? This is a hot section. The hottest gas from the combustion chamber impinges on this. It rotates the turbine module. So what you have here is integrally bladed rotor. It is also called as a blisk, and additive is one of the biggest sort of advocates for something like this, because you can truly get a weight reduction by making it into an integrally bladed rotor. So these are some of the Pratt & Whitney journey. And if you look at our entire organization, I work for now recently called Raytheon Technologies, which is both Pratt & Whitney, which is an engine, which you can see, I think you can see sitting behind me here. And then you also have all the other aerospace parts that go into an aircraft, as well as all the parts that go into defense technologies. We're called Raytheon. So several thousands of them have been made for visual rig and engine tests. A few of them have got qualified. Not everything has got qualified. So I'm sure you'll hear of many qualified parts. Today we have, if you'd asked me 5-6 years ago, there would have been a handful of parts. Today, after a lot of parts have been qualified by Federal Aviation Agency (FAA) to have these even in the engine, including stationary and rotating parts. So let me start with the preamble. I told you all of which I'm sharing today can be seen or available in this review article that was published earlier this year in the Transactions of Indian Institute of Metals. It's a Springer journal. They brought out an issue to commemorate the Platinum Jubilee year of the Indian Institute of Metals. So I think this came out in June only, and all what I'm speaking now can be found in that. But what I'm going to be focusing on is what are the different metal additive manufacturing techniques as classified mostly by ASTM and ISO committees. So there are many others people call, but primarily they talk of laser powder bed fusion. When we talk of additive manufacturing, literally laser powder bed fusion is a technology that has about 70 to 80% of the market share. And then you have laser direct energy deposition. You also have electron beam as a heat source. And then more recently, there's a technology called binder jet, which is neither electron beam nor lasers, neither wire arc. So there is no melting of powders by any type of heat source. Instead, what you have is you have sintering that is taking place. So you mix ceramic binders. It's akin to powder metallurgy technology. You mix ceramic and metal powder particles, and then you put them in the layer by layer process, as is the definition of additive manufacturing. And instead of melting and solidification, you're doing sintering of the powders and getting the near net shape part. So a close cousin of that is the metal injection molding, or the MIM technology. However, MIM does not fall under additive manufacturing because it is not a digital manufacturing process. By additive manufacturing, we always talk of the inputs coming from a CAD model or some other inputs coming in a digital form and getting converted into a code that the machine can learn and understand, and then layer by layer translating the near net shape, the net part shape towards a product by melting and solidification or by sintering. And what I'm sharing here are sort of some semi-quantitative attributes of each of the process, in case the manufacturers, in case companies, in case small-scale industries, people want to adopt this technology. You should know which of these processes has a form, fit, and function to your production line. or to the kind of parts that you're planning to manufacture. So powder bed fusion has a little bit of a limitation as far as footprint goes, in the sense that the most popular footprint is 500 mm by 500 mm. So, half a meter by half a meter. That too, the most popular is that. Of course, you have one or two machines, manufacturers who can make 1 meter by 1 meter. But then the larger the size, remember that your cost and the speed and everything is going to go down. However, the biggest advantage of laser powder bed fusion is you can get precision parts with net shaping, geometries with section thicknesses of the order of 100 micrometers. Position can be using powders or wires. Here you can see.
Ma'am, you can switch off your video because it is pausing and coming. Video.
Okay. Sure. Okay, so then is it better now?
Yeah, better.
Okay. Because of bandwidth, maybe. Let me just put it back on slideshow mode. Yeah. So, these are the different attributes. And as I said, it's just to give, lots of people will talk about it. I just said this is very important, especially if you're going to translate the research and development activities into a product. So it is better to start with a well-known, additive manufacturing technology, and then trying to see, what are the different attributes of it towards your final product. Of course, there's no guarantee that everything will work for every part that needs to be qualified. For example, a huge rotor that is there in a gas turbine. Obviously, I'm not going to spend my time and effort trying to convert that into additive just for the sake of it. Something works well in conventional manufacturing, we let it stay as is. If something is having a great advantage as shown in the performance indices, then we try to look for the right approaches to use it. And the starting step is this one, what I'm showing you on this particular page. So if you overall look at the additive manufacturing processes, I'm sure all the speakers will tell you about this in this workshop. It is a highly complex process. And what you can see here is there are at least 3 dozen process parameters that are needed in order to get a single density, even a simple thing like density without any porosity corrected. And then there are also a lot of process related. So I'm talking of this conceptual stage out here, which is what most of us in the research universities or the research lab start with, namely start with a new material or an existing material for a new design or for a new property that we want to do research on. We need to be cognizant of the fact that there are at least 2-3 dozen parameters, notwithstanding the fact that, we have to look for uniformity, the heat transfer, and then we're looking for all the metallurgical aspects, and then the residual stresses. So many things are there. And last but not the least, we have to go even from concept to the feasibility stage. I'm not even talking of developmental stage. Then you need to make sure that you have enough non-destructive inspection processes that will aid you in gauging the reproducibility and repeatability of even a simple coupon, for doing lab scale tests. So all these are very much in need of the day. But if before I even consider starting some work in this particular area, especially towards taking it from the conceptual stage to feasibility stage through to developmental stage, you need to be cognizant, as I said before, all the metal AM challenges. So what I've done is I've just put together a whole bunch of challenges that I have faced. I'm sure this is not exhaustive, but I've just put together a whole bunch because these are quite exhaustive in the sense this is not all what can I say? As I said, this is not exhaustive in taking into account every single manufacturer's challenge, but this is exhaustive all the same. And starting with design, starting with what are the manufacturing processes, the cost of the return on investment, and then development of or lack of standards, and then I said inspection technologies. And through the next hour or so, I'm going to be speaking about 10 of them, giving you examples of case studies in terms of mostly related to materials and mechanical properties and inspection. So I'll be talking about 10 different challenges, and in each slide that I'm going to show you, the challenge will be circled and numbered so that we can relate to it later when you want to ask some questions related to that. Okay. So typically, one of the biggest advantages I have seen of metal additive manufacturing, and most of the studies I'm going to be sharing are in repair and refurbishment of gas turbine hardware. It is also particularly relevant repair and refurbishment, especially in a workshop like this. I wanted to share because here I'm giving you a perspective of additive manufacturing on conventional manufacturing. That's why I chose repair versus new make, because in a refurbishment process, typically we're using a casting or a fabricated item or a wrought process. Just 1 second, I'm going to have a sip of water. 1 second. Yeah, sorry. So what I was saying is I'm going to put additive on top of conventional manufacturing process. So that way you'll also get the best of both hybrid manufacturing in the sense. So you'll know the challenges even further rather than making a new part out of additive. How do you remove the support structures when you're doing hybrid parts? How do you make sure there is a one-to-one correspondence across the interface, and so on and so forth. So at least personally, I have found the best low-hanging fruit to implement additive is in repair and refurbishment of hardware, of gas turbine hardware. And it is also having a lot of implication in almost all sectors. Automotive, for example, if you have a casting, and this casting is in low numbers and it comes back, for repair, then if there is no solution, all of these machinery, all of these products are discarded. So that is where additive comes to the rescue, because you can actually think of new research areas to actually implement additive, where you can have, for example, a more superior casting compared to the original casting and make the component life last much longer. So if you look at this chart, there's a typical chart we use in the aerospace industry. When you have a new make part, when the design engineers are designing a new product, a gas turbine with different so many different conditions for the individual turbo machinery parts, then the acceptance standards are very high. I'll give you an example. If I take this blade that I showed you earlier when the video was on, then that blade is a single crystal. Obviously, we need single crystals because they are the heart of the gas turbine. They are extremely superior in terms of creep resistance. So that's why we spend a lot of money and effort in generating the high pressure turbine blades with a single crystal. Now, when it comes back after repair, after service engine operation, let's say 1 year, the flight has flied up and down, up and down. Obviously, you're going to have tip loss, tip oxidation because of the high temperatures, and so on and so forth. And so, can I discard this whole single crystal when the rest of the blade is actually looking intact and pretty good? No, you definitely need a solution for it. Otherwise, we're wasting a lot of time and effort. So, when you come to the first line below, repair minimum accepted standard, here you're actually going to be able to say, let me do a weld repair, at least of the airfoil tip. And when we do welding, obviously you're going to have solidification rates that will render into an equiaxed structure. And how can you have equiaxed on a single crystal? Of course, that is how it is being done now. And that is how we are flying back in the planes with the repaired single crystal turbine blade. So what happens is the acceptance standards, we lower it and then we keep lowering it and we extract the maximum out of the part until end of life. I think it is true for any sector of structural engineering materials. Repairs continue until either the part cannot be restored to minimum acceptable standards or the repair cost exceeds the new part replacement cost. Or if there is a completely irreversible material damage, microstructural change, that it will no longer meet your requirements in terms of the mechanical properties, then we discard. So until then you can repair. And so I'm going to take this case studies because for highlighting the challenges and how we overcame and how we can use metal additive manufacturing as a unique solution that no other conventional manufacturing technologies can offer. That is the low hanging fruit. Of course, we can always try to keep making new parts. And just to give you an idea, in slide number 10, I'm sharing that I have personally worked on several repairs, as well as new make, but a large amount, over about 2 dozen alloys that you can see here, many of which you will recognize because they're all popular alloys by now. So I worked on, hot section blades, tips, nozzles, and so on and so forth, and including in the automotive industry, conformal cooling using maraging steels and so on, using all three, laser powder bed fusion, direct metal deposition, and electron beam melting on broad range of alloys, nickel-based superalloys, cobalt alloys, aluminum alloys, steels, and titanium alloys. So I'm going to start with this example. So this dates to 2015. And when we proposed this idea, wherein the stage 1 nozzle or vane of a gas turbine, they underwent hot corrosion. And it keeps happening all over the world in several gas turbines, especially for industrial gas turbines, wherein the petroleum or the fuel that they use to combust is not very, very pure. It has all kinds of, and when combustion takes place, emission takes place. We all see emissions, all sorts of carbon monoxide, carbon dioxide, sulfur dioxide, so many other emissions that will cause what is called as hot corrosion. So you can see the vane, the trailing edge of this stage 1, the first section to see the hottest gas. You can see this like a moth-eaten leaf, and it has got severely damaged, and all these veins were discarded. So what we did is we came up with a solution 6 years ago, as that time additive was not such a big buzzword, but we were a little ahead of time, I would say, for this particular series of experiments and qualifications that have been done for the gas turbine hot section components, wherein we proposed, let us do two things. One is, let us cut off the damaged part and let us make an additive laser powder bed fusion insert or coupon, and let us join them by welding or pressing. The other thing we said, let us also use direct energy deposition, laser DED, and cut off this part, damaged part again, and let us build on top of the existing nozzle, because this portion seems to be quite good near the trailing edge. Let us build using direct laser deposition the part to the near net shape with all the cooling holes and so on. So fortunately, during that 1 year, at least 4 master students between 2015 to 17 worked with me, and some of the work we've been able to present in some conference proceedings and some publications, and that is what I'm sharing here. So what we did is, as I told you, the base alloy was an investment cast FSX 414, that is a cobalt tungsten alloy, onto which we said, let us cut off the damaged part and near the trailing edge and deposit laser powder bed fusion cobalt chrome moly, as you can see in the schematic out here. Then after this geometry is joined, let us weld these two together, the cast FSX 414 and the powder bed fusion cobalt chrome moly. Let us manually weld it, and then let us implement the the part back into service after post weld heat treatment. So what is the starting step out here? The starting step is to actually map the process parameters to give a part with 99.9% density. So that is what this is, cobalt chrome moly, this one, and this is being attached to an investment cast FSX 414 we looked at, I showed you a couple of slides ago, the kind of complexity you have in the powder bed fusion technology. So what we did is we optimized, this was a master's thesis of a student from PSG Tech. We optimized very quickly in February and March of 2015, the a design of experiments based on laser power, scan speed, and layer thickness in the powder bed fusion process in order to actually get the in order to actually get a dense part. So our y equal to f of x is going to be, x is going to be all this, and the y is going to be the porosity. That is, it should be as dense as possible, because this is a hot section part. We cannot afford to have any, stress concentration related factors by having something with defects, already inbuilt defects, known defects. We cannot afford to have. It has to be a dense part as much as any conventional manufactured process. So having done this, then we got a whole bunch of microstructures. When we started, it was quite scary because we did get a lack of fusion at every single layer, a lot of porosity that has crept in, either due to the entrapped gas or due to moisture or whatever. But soon enough, we optimized the process parameters and we tried two conditions, one with hot isostatic pressing. And normally this hot isostatic pressing is done for all the hot section parts, irrespective of what part it is in an aero engine, so that you delay the fatigue failure due to inherent defects. And typically hot isostatic pressing is done to close the pores in the grain boundaries in order to enhance the creep resistance of the material. So we tried both with HIP and without hot isostatic pressing, and based on this DOE, between a month and a half we were able to go from this particular top row to the bottom row without HIP. So this material here at the bottom most became our new norm in order to test other factors towards qualification of this particular idea of having an additively manufactured near net shape part and an investment cast dissimilar material, because remember, this is cobalt chromoly, that is cobalt tungsten alloy, both of these joined together. So that is what we proceeded. And then having got this, next we went into the microstructure. In this particular cartoon, you can actually see the layer by layer deposition taking place. That is a laser beam out there. The laser beam is actually melting, and you can see one layer is coming, another layer is coming in, actually melting the first layer. The first layer is the one, first to be deposited on top of the substrate. And in this particular application, we did want a isotropic microstructure. In some applications, we need a directional microstructure. In this case, we looked at the three-dimensional view of the microstructure. You can see the weld pool like this to the left-hand side cartoon, and the right-hand side, you can see this collage that has been made. So this has all the weld pool that you see here. There is a one-to-one correspondence between the left and the right being the actual real coupon that is being tested, and very fine interdendritic microstructures you can see here, very, very fine. So of course we went on to analyze the as printed structures, and then you can see here dense without hipping dense sample. You can also see the etched microstructure here. And then we went on to observe whether there were any micro cracks. Yes, there were some micro cracks. It is impossible to make a material without, without any defect at all. And then if I blow up the weld pool boundary, what you can see here is fine athermal HCP plates, which can only be discerned in the TM, but nevertheless, we were able to see it in the SCM. And if I look at the heat extraction, from this is supposed to be a video, but it's okay. It's just coming like that. So you can see that there are domains within the weld pool, within one weld pool. As you look here, there are domains of similar orientation out here. And then this sometimes translate between one weld pool to the other. So further, and then there were athermal HCP plates between 600 to 1000 nanometers, less than 1 micron, running all the way through. Remember, the metastability out here. So that is sort of the second challenge I'm going to come to. But before that, I'll just show you the different advanced characterization that we did to discern the, what is happening in this material. Is it in a metastable state or is it in a stable state? And what do we mean by that? Will there be thermal stability? So to summarize a microstructure, in the as printed condition, you see a thermal epsilon HCP band in a gamma FCC matrix. Of course, there are pockets of, you have a whole bunch of precipitates out here. We have discerned what is the nature of this precipitate from this high angle annular dark field image, and I'll be sharing that with you shortly. So then we went on from the microstructure. We need to give the pre-weld and the post-weld heat treatment, because remember, we are going to weld this particular part to the cast FSX 414. And here, as I said, one of the biggest challenges, yes, we were able to do a whole bunch of heat treatment optimization. Again, this is another master student's thesis, in order to get a nice recrystallized microstructure, such as what you see in the right. And here we kill two birds with one stone, namely the heat treatment that is necessary for the microstructural evolution of the additive cobalt chromoly versus versus the actual microstructure that is going to correspond to the best mechanical properties. So when we look at the microstructure, it gives a nice fine grain structure, not more than 35 microns. And here we're very thrilled about it, because fine grain structure means very good strength. But also we're a little worried, and that is challenge number 2 that I've highlighted here, because any fine grain microstructure is going to be a bane for creep response. This is going to be really bad. It's going to be creeping like crazy, because grain boundaries are diffusion paths, and especially at temperature. And but nevertheless, the challenge I'm trying to highlight here in number 2 is must pay attention to the heat treatment optimization, which actually is a blessing for via additive. Because of the rapid solidification, you are able to get different microstructures that are conventionally not always obtainable. Okay, I just wanted to highlight one point. Okay, so I wanted to highlight one point in this challenge 1, which I forgot to. I'm not referring here to the aspect of getting dense samples. That is almost a no-brainer these days. With the kind of software development that has taken place by additive manufacturers, by Magix, by ANSYS, by several people, we are able to get a good parametric, conditions to get dense samples, irrespective of which alloy in the series of alloys that that I showed you. However, what is the true challenge that we faced here is, despite running through a very exhaustive DOE, design of experiments, we are not able to get statistically significant numbers between these energy densities in order to finally choose which of these process parameters will be best suited for our application. So what I'm saying is, all of these give dense parts greater than 99.5% density, in which case, which of these energy densities and hence these process parameters will you follow? So I'm not saying it happens for all alloys all the time, but challenge number 1 in not being able to meet a statistically significant result is something to recall and to think about. And, it was a challenge for us, because all we had to do the entire project in less than 1 year, right from the concept to the design stage. Okay, so I'll go back to challenge number 2, which we just completed. Namely, what you have is a microstructure which is metastable. I've been able to get a uniform isotropic recrystallized microstructure by combining the post-weld heat treatment process with the with the heat treatment that is necessary for this particular alloy via additive manufacturing. So the microstructure isotropic. So this is the electron beam scattered EBSD map, diffraction map, which shows you there is no preferential texture or orientation after doing this heat treatment and this particular condition. So then we move on to the mechanical properties. Here in this particular case, if you look at the left-hand top chart, then you can see yield strength out here, point to percent yield strength, UTS, percentage elongation, etc. And you can see as compared to the cast, investment cast FSX 414, that is the red colored, brown colored histogram, our material, which is the green colored no hip cobalt chromoly, is almost 40% stronger at temperature at 930 degrees centigrade. Now, it is also, you can see, whenever something is strong, we expect the ductility to drop drastically. So what you can do, what we can see is, luckily in our case, the ductility has not dropped much. So this itself is a big progress, in terms of having high strength and no loss in ductility. However, is it a cause for concern? Maybe it may not be. Why it may not be? Because the fine grain structure that is already there, that is a fine grain structure that we've got because of the heat treatment, that can lead to very bad creep response. So immediately we evaluated creep, and luckily for us, the black colored curve, which is nothing but no hip cobalt chromoly, that is this material, and that is the material that we have optimized, is a very slow creeper, luckily for us. And then whereas all the other alloys and all the other systems are, I would say, all the systems, every single mechanical property at temperature has to be evaluated. So why is this a challenge? This is a challenge because in some cases, as you all know very well, the mechanical properties can be orientation dependent. Modulus can be very low in one direction or orientation. It can be higher than the nominal value in the other orientation or direction. Namely, and I'm only talking of 90 degrees two orientations, transverse and longitudinal. However, it depends on the application that you're working on. And so you need to, it's definitely a challenge because typically I would say a thumb rule is the transverse is always higher in strength as compared to the longitudinal orientation. But what is challenge number 4? Challenge number 4 I'm saying is, despite the fact that you have to evaluate mechanical properties at temperature, at various builds comparisons, what you also need to be cognizant of is something like the hipping. That's why I'm putting this as challenge number 4. Something like hipping may not always be beneficial for the additively manufactured materials, though it is very beneficial for the casting. I know that, but for additive manufacturing, hipping, role of hip can be either positive direction or it can show a debit. Okay, and then of course it's not suffice. It doesn't suffice to do room temperature mechanical properties. The mechanical properties have to be evaluated at the temperature of the operation of the part that is intended in order to give the true meaning. Even in the papers, even if you're just going to write a publication, then you need to keep in mind all these as important challenges that you need to go forward with. So I'll again share you an example of that. So in our particular case, going back to the case study, we were lucky that despite having a fine grain structure, since it was isotropic, there's no problem. When we did the creep test along with that, along with the samples sent by, along with the samples sent for various orientations, we were able to find that we had a very slow creeper in this particular cobalt chromoly without any hipping, the new material that we developed. Of course, can we stop there? No. In order to proceed further and evaluate the thermal stability, we have to have a thorough understanding of the microstructure then and there. So this is the work of yet another master student from NIT Trichy during the same time frame, wherein he was able to actually help us with deciphering what is there present along the grain boundaries and why is it a slow creeper, this microstructure. It should have been a very fast creeper. So, so etc. etc. So in this particular case, we found it to be a much slow creeper because all the grain boundary, is pinned by these precipitates, black and white. I won't go into the, details of it except to say that the fine grain boundary precipitates come on aging actually. And then the next challenge number 5, now we are coming down to it. What does that prescribe? All of you know the surface roughness is a big issue in additively manufactured components. Surface roughness is, even if it is an external surface, you can add a little more and then you can conventionally manufacture that component without having a high surface roughness. It can be very low. But however, you all know that surface roughness is especially internal to the geometry. External, at least you can give. If you look at the surface, I can add a little bit more here, and then I can, like this. Let me just see if I can annotate here. Don't know where the annotate went off. I think it's, oh, maybe this. Okay, it's not coming. It's okay. Like, I'll just close this. Now, I just thought I'll draw and show you. It says I can annotate, but let me rub it off. Okay, so what I'm saying is out here, if you look at the, I can give a little more print and machine it out. I can do process parameter optimization out here. But, if it is a conformal cooling hole or a fine cooling hole in a blade, turbine blade or a vane, how will I machine it out? There won't be any accessibility. So surface roughness is a big challenge to be overcome. And how we overcame this particular challenge is to partner with our CFD colleagues. So we said, when you have a surface roughness, internal cooling hole surface roughness, and with this kind of morphology that you're seeing out here with very, very sharp corners, this can be KT factor or stress concentration factor and cause premature failure. That is number one. The second challenge is that when there is a roughness in the surface, you all know that the circle without roughness and with roughness, the one with roughness, it will have a more constricted volume. That means the amount of fluid that can flow to it will be reduced, not to mention the stress concentration factor of something as sharp as this. So what we did is we did how we overcame. So we calculated, we made a little bit of an intelligent overcoming of this challenge. We calculated how much is the pressure drop that can occur for the compressor discharge air which goes through this hole. Took our CFD colleagues' help and they calculated the pressure drop. But as it turns out, what we also found is that the parameter optimization of the roughness did not give such a smooth and a reliable roughness inside the cooling hole. So we took the pressure drop calculation by the CFD colleagues to our advantage. We slightly enlarged the cooling hole dimension on a case-to-case basis. Of course, needless to say, if you change the design and all, you have to ask the permission of the designer. And then we calculate the pressure drop. And then since there was a pressure drop, it could lead to hot spot. That is very dangerous because you can have premature stalling of the engine. So then we increased slightly the cooling hole dimension and then printed it and then was easily able to solve this particular problem. Okay, so another fifth challenge is that of surface roughness. We move on to the sixth challenge. So having addressed these, what we did was, the next we try to build more coupons. We call this as a coupon, trailing edge nozzle coupon in the build plane. However, when we try to do that, look at this challenge number 6. Challenge number 6 is very, very important, and namely that of residual stresses that creep into the component. Now, all of us in the welding world would have definitely always come across residual stresses as the weldment will be in the tensile stress state. However, here, additive is a layer by layer welding and solidification process. You see, when we printed just 2 of them, when we try to remove it from the build plate, because of the residual stress, if you can see this red circled bullet point, there we were not able to remove it from the build plate without causing any damage such as what is shown here. So what is the fifth biggest challenge? Residual stress. Sixth one, what we did is then we did a flat coupon. We estimated the residual stress by a through thickness XRD, X-ray diffraction sine square psi method. But that is not good enough to tell me what are the stresses inside the cooling holes. Wherever, it doesn't tell. So we had to, alongside, we had to establish the residual stress in the geometry by numerically, by using finite element analysis. We took the geometry and we started by, by taking the physical metallurgy inputs that feed into that. And this was a collaboration with one of the NITs, actually. And then we came up with an idea, establish correlation of residual stress distribution for geometric and build parameter, and validate using the additive manufacturing tool. And with this, what we did was we put another set of struts. We said we will add a few more. In order that we are able to remove 10 or 12 or 15 parts from the build plate without it having to face the difficulties as is shown in this particular picture. Namely, while removing, there is so much of tensile residual stress that you are not able to use a EDM wire cutter to remove it in a smooth manner. Okay, so residual stress is another very, very important technique. Next, we come to, how did we measure it? I only wrote here, experimentally establish the residual stress along and perpendicular to the direction using XRD through a thickness measurement and through thickness measurement, etc. Establish correlation of residual stress and correlate it with the finite element analysis. So what we did was we took the coupon, did sine square psi method, and then you can see the actual part here on the surface through thickness. As printed condition shows a tensile stress of almost 250 megapascal. And then when we went through the complete heat treatment, and this is a cycle that I showed you finally, the recrystallized microstructure, we were able to see the sinusoidal behavior of the residual stresses. And finally, in this 1150 degrees centigrade, there is little or no stress. It is almost neutral. You can see from the last slide in the picture. And that is why we chose this particular picture. Though I showed it in the beginning, chronology wise, this is how we chose it. Okay. So then the seventh challenge now. Seventh challenge is really an important challenge. It's also a very, very thrusty research area. Those of you who have that kind of a background may well take this up. The research area here, namely, since the whole business of additive manufacturing is near net shape part manufacturing, how come we still use ASTM test blocks and test standards for evaluating the mechanical properties? It can be a big challenge in more than one way. Why? Because the true development of a part like this, like a cylinder and then machining out dog bone specimens, may not be representative of the process parameter optimization that I spoke to you of in challenge 1, vis-a-vis the actual part geometry like this. So there may be large variations, and that is truly a challenge we are facing in small scale testing. ASTM and several of the committees are taken this up in a big way. Small scale mechanical testing, is very, very imperative to develop and to establish in the next 10 years, in order to truly qualify and acceleratedly qualify additive manufacturing. So, but what is the other challenge I'm highlighting here, apart from small scale testing, is the fact that, okay, what did we do in this particular case? We joined these coupons to the FS641 nozzle. Then we welded it by manual TIG welding. Then we took samples from across the weld. And you can see here the left hand side and the right hand side. So the weaker part is the investment cast FSX414. Both the tie line, you can see the blue color dotted line, the tie line representing this particular interface between the additive and the cast across this particular line. Both the additive part as well as the weld joint are intact. The failure or the weak zone happens only in the investment cast part. So this is another very important challenge you need to actually watch out for. And then I move to the next challenge. The next one is again very, very real. I touched upon this briefly earlier. Namely, how do the properties, mechanical properties in microstructure compare between the bulk coupon? This is a 1 inch by half an inch by half an inch coupon. And these are cylinders in two different orientations. Namely, you've got a transverse orientation, you've got a longitudinal orientation for doing mechanical testing. However, what implication, I spoke to you about the mechanical property and the differences it can have between the bulk within quotes bulk vis-a-vis the part the part thickness. Here, what I'm highlighting is the importance of heat treatment in differentiating between the bulk and the actual part. Okay, so I'm going to give you a couple of examples. One is this. This is a cranial implant made of Ti-6-4, titanium 6 aluminum 4 vanadium alloy, a popular powder bed fusion electron beam melted alloy in the aerospace industry via metal additive manufacturing. Titanium is very inert in the human body, so it is used a lot. And you know what is the challenge that this stares out is this particular cranial implant with a section thickness less than, you can see here the support structures. You can see all the support structures there. These will be removed very easily. Finally, only the implant will be there. Where typical Ti-6-4 heat treatment, stress relieving heat treatment involves heating in vacuum. Now, what we try to do is we said in the interest of the urgency, for example, an implant like this is typically given to a trauma case. You know, in this particular case, one of the was for a, I think, trauma in the sense it was a head injury or something like that. So immediately the doctor wanted the cranial implant. We made it overnight by taking the DICOM image from the CT scan that the doctor had sent. However, what happens is you need to heat treat in vacuum, and that does take time if you don't have a vacuum heat treatment right next door. So we wanted to do the effect of heat treatment optimization in air versus vacuum, and this was a small BTech students project from BET Mishra in 2019 that led to this particular study, and you know how we overcame this particular challenge number 8, but definitely brought into the picture that this was a genuine and very important challenge. So we took the implant itself. You can see cut pieces of the implant, and we took the bulk also. You can see these two are the bulks, and you know we just looked at the effect of the microstructure here between the edge and the center of the thin wall implant structure. There could be variability in the microstructure because, as you know, in Ti-6-4, the oxygen at the edges, the pickup of oxygen is more, especially in thin sections like this. And once the oxygen, you know, gets picked up, then there is a change in the alpha beta titanium structure along the edge. So that is another challenge. I'm not going into the details of it. You can find it in this publication. But that's a bigger challenge to also look at. Should we do water quenching? Should we do air cooling? Should we do furnace cooling? Should we do direct aging? Should we do a simple stress relieving? All these are very, very preliminary, very, very important questions to ask before carrying out the respective heat treatments. Okay, so because it can completely change the microstructure from the left to right, especially in titanium alloys which are prone to oxygen affinity. And if microstructure is affected, it will definitely affect the mechanical properties. You know, provided the application there is one that requires, requires the bulk and the actual part to be the same, right? Okay, so I come now to the 9th challenge. And what is this challenge? This is again, we have faced this several times. Again, when I take a bulk coupon and estimate the porosity and the mechanical properties, here you can see the same 1 inch by half an inch by half an inch coupon. And if we cut it up, the porosity values are between, hardly anything on the top right-hand side picture, less than 1% definitely. Whereas the same thing, if I take into a part as shown in the turbine blade internal cooling hole out here, typically what happens in an additive, you have a CAD model. CAD gets sliced into CAD gets sliced layer by layer, and this G code is fed into the software. But by chance, one or a few lines get missing, then you will have an effect something like this. See, you have a completely missing plane of atoms, and you also look at the porosity on the top and the porosity here. This is quite different. This and this have no match at all. Whereas we would finish all our qualifications with respect to this microstructure and this mechanical property. Okay, so this is a very important challenge. Now I come to the last challenge. Last challenge I told you, it was, you can just watch this embedded video here. It is due to have quality control checks in situ. All these while we were talking of ex situ and destructive mechanical testing, mechanical property, and so on. So here you can see the top picture, in situ thermal photodiode, thermal imaging along with the scanner. The top picture is able to pick from location specific, splatter or keyholing effect. Whereas the bottom video that you're seeing here is pretty good. It is, you don't see any splatter of liquid out here, and it is able to do its job and cause a good product. So what you can see here is, you can see as a function of length, how the structural integrity is going to vary. So you have optical optical detectors, optical thermal imaging, thermal imaging hardware, which now people are using to pinpoint some of these areas. Okay, of the 10th challenge. So I've come to the end of this. I think I have probably finished in an hour. If we can pause here and take some questions, and then I do have other case studies which I can share afterwards, or how would you like to go about it?
We can have some questions, madam, first.
Yeah, because I wanted to, end this challenges part and then show you more examples. Taking all these challenges, I can show you, we have some more time, how we have overcome some more parts that have been taken for qualification. So, notwithstanding all these 10 challenges, so what we did is we qualified not only the cobalt chrome moly that I showed you in this case study, but we did qualify a number of components by utilizing this approach right from day one, till whenever the project got completed, which is maybe 10 months or 12 months later.
Okay, fine. So the participants, if you have any questions, you can post, then ma'am will continue after the question answer session.
Can you ask now?
Yeah, please.
Yes, ma'am. This is Anand Runal from SSN Engineering College, Chennai.
Hello, good morning.
Good morning, ma'am. Actually, the current cooling hole in the turbine blades, how they are made?
So right now you do investment casting.
Okay.
So by investment casting, you have a core like this. Okay, the ceramic core is there. The blades are already designed and these are made. That is in the high-end turbine blades. In the latter sections, that is the sections which are not so critical, which are not single crystal also, then you make them by any of the conventional manufacturing hole drilling methods. Lasers are typically, it is used, lasers are used.
Okay. But through the cooling hole, does the fluid air go or any other fluid? I'm not aware of it.
I'm sorry, I didn't follow your question.
Inside the cooling holes,
Mm-hmm.
what goes through, fluid or air? I mean,
No,
any
there's no
specific
fluid. No,
cooling?
these are all.
Gas
Let me show
turbine.
you the video. Yeah, I'll just come on video. So if you can see the blade in my hand, I don't know if you can see the cooling hole.
Yes.
You can see very fine holes here.
Yeah.
And you can also see it's practically, I'll point here also, you can see the back side also, it is completely hollow.
Okay.
So since it's the first stage and the hot gas impinges on it, and typically these will have a thermal barrier coating.
Okay.
So because the temperatures exceed 1600 degrees centigrade, much higher than the melting point of the metal. So, what you have is you completely, the entire aircraft engine, from the compressor, from the fan blade till the exhaust, it is practically, I would say, a heat exchanger. So everywhere you have compressor air. From the compressor, the fan ingests the air from the atmosphere. The compressor blades, low pressure turbine and then high pressure turbine, keep on volumetric compression takes place. Okay. And when the part of the air is sent as a bypass air, not full air goes in, the air gets bypassed, and that air is the one which is used for cooling all the combustion chambers, compressors. It is used as pneumatic for various functions. And then that air is the one which internally, remember, even if I have a thermal barrier coating here, thermal barrier coating can only insulate from the heat. It cannot protect completely, it cannot protect the blade from heating up because it's a metal with a good thermal conductivity. So the air inside, you send bypass air through this, that can extract away the heat. You need internal cooling always when you're having high temperature turbo machinery.
Okay, okay, ma'am. Thank you. And you talked about cranial implant. In that, you told about titanium-based implants, right?
Right.
Titanium has little bit higher density, compared to other materials. Does the patient feel comfortable when you use a higher dense material especially for cranial kind of implants?
Yeah. I mean, titanium is very, very routinely used. Cobalt and titanium are used. In fact, even more dense cobalt is used in the knee replacement joints, hip replacement joints. Titanium is used in the dental implants very routinely. And then, all these are used quite routinely because of the inertness with respect to the human body.
Okay.
Osseointegration is pretty good with these materials.
Okay. And you told about some support structure used for cranial implant printing. Is the support also made of same material?
Support has to be made in all, not only for cranial implant.
Is it also made of
Almost
titanium?
all the additive manufacturing technology support has to be the same material. Remember, it is a layer by layer process, no?
Yes.
So how can I build a support
So
is
we have
done
to
concurrently with each layer of printing.
okay, so we have to do some post processing to remove the supports.
Yes. Typically, it's very complex. In this, it is easy because the way we build the support structures is it will not be so, strongly held. So you can EDM wire cut it, or you can use a mallet and sometimes remove it if accessibility is there. But if accessibility is not there and the geometry requires my support structure in very intricate holes, then there are some abrasive polishing that are being done to remove the support structures. Yes, definitely all additive manufacturing technologies, especially complex geometries, need, especially larger and larger you go, you need more support structures. Overhangs, for example, because a liquid will fall down, right? There and all, you need support structures. And in those cases, you need to do post-processing. Even otherwise, you need to do post-processing to, make sure that the surface roughness, surface features, etc. are maintained.
Okay, ma'am. Thank you.
Ma'am, there is one more question in the chat box. So,
Sure.
Dr. Dheeraj was asking that titanium additive manufacturing, whether it needs vacuum or not, he's asking.
Well, it's nothing to do with titanium. It is to do with the additive manufacturing, metal additive manufacturing technology that we are using. Remember, I shared this slide with you people. So, for example, laser powder bed fusion. The lasers are typically 1 kilowatt. Now you get up to 1 kilowatt. Typical lasers are, 300 to 400 watts. And this entire thing has to be done in an inert atmosphere. There is a build chamber, and inside that, it has to be argon, sometimes nitrogen. You need to have an inert atmosphere because otherwise, precision, there will be oxidation of the metal powder. Okay. Electron beam melting is also done in a sort of an inert atmosphere. Only direct energy deposition and a few others, I won't go into the details of every single, you don't need an inert atmosphere, irrespective of the which material you're doing, because you have to do extensive post-processing. So the size is also very good, the speed is also, throughput is also very good. The nature of, for example, the titanium chamber, titanium chamber, ISRO also put it, and then, a lot of bottles in the space shuttles are all done. Large structures, NASA, everybody is using, even VSSC is using. So in those cases, they will be doing post machining using conventional manufacturing. But so it depends on the nature. It is not so much the material, but with respect to titanium, I think the question, I would rephrase your question in a different way. Titanium is very, very prone to oxygen sensitivity. So the powders have to be powders or wires, whatever, but mostly powders, I would say. You have to take a lot of care to handle them, to make them without any oxygen impurity, because titanium alloy is very, very sensitive to oxygen pickup, and the microstructure and everything changes, both in conventional as well as in additive manufacturing. I hope that answers your question.
Yes. There is one more question in the chat box.
Sure.
You correctly told that it's difficult to adopt ASTM standards for additive manufacturing process optimization, but what could be the other standards where we can go for?
Actually, you don't. I didn't say that it's difficult to adopt ASTM standards. Let me make a small correction in that. All I said is we don't have ASTM testing standards for very, very small scale miniature testing. So supposing, I'll give you an example again. This is 3 inches, okay? You can see the blade, right? Are you able to clearly see it? And if this is what I have made using laser powder bed fusion in a layer by layer process, okay, I might have put a support structure somewhere here where there is, I might have put a couple of support structures here. Let's say I've removed this, this is my part. Now, if this is my part and this has a section, very small section thickness here, a slightly different section thickness here, a different here, a different in this angel wing, it is completely hollow here. So this, this is practically hollow. Then there is no, it is not correct to use, actually I had the cylindrical sample somewhere here. I'm trying to show, somebody took it off in the morning. Let's say this is a cylindrical sample that a dog bone specimen, like how, let me show you that. It is right here. I'll show you out here. So if I'm going to take this one and machine this out into this dog bone specimen as per ASTM standard testing, that is not going to help me in exactly evaluating the structural integrity of this near net shape part. That is what I said. So to answer your question, ASTM is coming up with a number of standards for, for revising to suit additive manufacturing, to suit small scale testing. And a lot of researchers all over the world, including we ourselves, are working on some miniature sample testing, not just for room temperature testing, but other ways of testing, like, not just uniaxial tensile or compression, for creep, for fatigue, for fatigue crack growth. How do we remodify the whole mechanical testing at temperature to suit the true geometrical requirements as imposed by a near net shape manufacturing process? So there is nothing to answer your question. There's nothing that we can fall back on now. But I will definitely tell you that for each of the case studies, including this page that I'm showing you right now, including the build plate on the right hand corner for this particular geometrical part, we defined and redefined, and we had a benchmark. What was my benchmark? My benchmark I don't have with cobalt chrome moly. I don't have cobalt chrome moly because cobalt chrome moly is not an aero section, a gas turbine or an aero engine part in that sense. But my nearest equivalent for cast FSX 414. So when I'm implementing this in a case study like this, then I took this as my reference. And I said my additive part has to be better than this. But a lot of people are working on developing standards, to answer your question. Some standards are already out there, but there's still a very, very active research area that is out there open, and a lot of people are writing proposals, a lot of funding for this particular area, as well as this particular area, inspection also.
Okay, thank you,
Does that
ma'am.
answer your question? Yeah,
Thank you.
sure.
Yeah. Any other question? I need a small help, ma'am. Actually, we were also trying to do some metal components actually using Inconel 718, but there we are using the laser cladding process. But we had just started working about 2.5 years back actually. But 718, IN 718. So we were thinking of residual stresses also. We were unable to manage, means to evaluate these residual stresses. We are also facing the problem actually.
Okay.
So, is there any other method? Because right now, whatever the components which we made, we were doing residual tests using XRD from IIT Bombay, but they were not very encouraging. So I don't know whether we are doing mistake in the deposition or the process in which we are adopting also we are unable to understand it.
No, but what is your question? Why, see, residual stress evaluation, there is X-ray diffraction, science quasi, or there is neutron diffraction, which is not very easily accessible because in neutron diffraction, the penetration depth is a little bit more. But the fact of the matter is residual stresses, experimental measurements are only through thickness. That means it can go from the surface to the bulk on a flat sample or flat or whatever. But, and it'll only give you surface values or up to a few microns. So you need to keep on removing material. However, that is only the experimental validation of a coupon level to qualify your process parameters. It says nothing about the geometry. So in this particular geometry, if I have to measure residual stresses before I welded it to my cast FSX 414 or develop these DFAM, like these struts that we designed to be able to remove it without this distortion, for example, or even residual stresses are really very dangerous because it can completely result a very thin section in additively manufactured such as this blade. It can actually change the dimensions, and so on and so forth. So the only way to correlate is by doing some kind of a numerical modeling. So establish, perform transient thermomechanical finite element analysis to actually predict the residual stresses completely in the component level, validated by experimental validation using science quasi technique or neutron diffraction or whatever method you want to use.
Okay, fine. Thank you. Any other questions from the participants? Okay, if you don't have, then ma'am will be showing some of these case studies, or is it done, ma'am?
Yeah, it's up to you. It's we have another 5-10 minutes left to 11 o'clock.
5 minutes more, actually.
Okay, then shall we take a couple of questions and close it? Because I don't think I can finish running through a case study in 5 minutes. It may take at least 10 minutes.
Okay.
So are there any other questions?
Any other questions? The participants, if you want to have a particular question, you can post it actually.
Okay, if not, I'll just speak a little bit more about the importance of the challenges in the 5 minutes.
Sure.
As I said before, these I can definitely you can take a copy of this. This is the DOI of this particular review, as I mentioned. I can also share it with you, Professor Gupta. The fact of the matter is, when you're all doing research in this particular area, there are plenty of research topics. What we normally do is we take at the coupon level, we establish some mechanical properties, microstructure, very simplified, or maybe some corrosion studies, some creep studies, some phreatic studies. The fact of the matter is, when we have to take it from this level to accelerated production, then, there are lots of challenges as shown in this particular chart. And that is when it is always good to tie up with, look the research opportunities and problem solving for adoption only comes up when you're actually correlating these two. Just by taking the coupon level and studying. So for example, I think challenge number 3, I told you about the metastable microstructures. For example, cobalt chromoly is HCP, but it came off as an FCC because of the rapid solidification. So that itself is, and then the segregation. And Professor Gupta, you spoke about IN 718. Despite having almost 250 papers, publications world over, maybe even more, that have actually been published in the last recent 3 years, including the COVID year, we still don't know why there is a poor high temperature drop in the ductility. We still don't understand why there is a poor creep rupture knot sensitivity at elevated temperatures. So Inconel 718, in spite of all the studies that have taken place, it's one of the oldest additive manufactured alloys. It has still not reached qualification to any rotating parts because of this issue. So it is very important to look at research areas that are contemporary by academic people, by students, and give them more practical problem, because additive manufacturing is a field which is more closer to the practical engineering compared to even other and new alloy development, for example. It is very, very easy to develop a new alloy because powders manufacturers are able to make powders easily these days. And to look at the adoption of new alloys, by which I don't mean esoteric new alloys, that can also be done, but more ones that can be adopted to, let's say, a cryo engine, and then take it forward by addressing some of the challenges. Okay.
Yeah, thank you, ma'am.
Sure.
If you don't have any other questions, then we should thank Dr. Deepa Srinivasan. Thank you very much, ma'am, for your
Yeah,
wonderful
thanks again.
expertise.
Yeah.
And can I share your mail ID with these two participants? If they want to post some questions, they can post it actually.
Yeah, sure. I would prefer, yeah, you can be the moderator, and
Sure.
then
Okay,
yeah.
let them write to me. I can send it to you.
Yes, that'll be better.
Better.
Then
Yeah,
yeah, sure.
yeah.
Thanks a lot. Have a good
Thank you
week.
very much.
Bye-bye.
Thank you very much, ma'am. Thank
Yeah.
you. Okay, friends, there is a small announcement. What I want to inform you is that the next lecture, which is going to start at 11:30, it was supposed to be delivered by Professor Puneet Tandon, but unfortunately, in the early morning, his father has taken his last breath, actually. So he was traveling from Jabalpur to Kurukshetra right now. So he will not be able to deliver the lecture, but in his place, Dr. Jitendra Katyar from SRM Institute of Technology, he works on surface engineering. He will be delivering the lecture at 11:30. So the link will be the same, but the person who is going to deliver the lecture will be different. So this is for your kind information, and we'll meet at 11:30. Thank you, everyone.